Hello all, a quick introduction of myself. Yeah. So, hello all, a quick introduction of myself. I'm Shubham, and I'm in my PhD second year. I'm pursuing my PhD from IIT Gandhinagar in the Department of Electrical Engineering. So, right now, I'm the TA for this course, Digital Circuits, offered by Professor Shantanu Chattopadhyay. So, we will be solving some questions today. So, the topics we will be covering today are uh, arithmetic circuits and CMOS gates. So, I will give you about 3 to 4 minutes to solve this question. This is a fairly simple question. So I will solve this question. I hope everybody solved. So here A bar B represents this intersection. Similarly, AB bar is this region. Now we have AB, which is this region. So if we add all of them, which is equal to A plus B. So the correct answer is A. Fine. Moving on to the next question. So I will give you 5 minutes to solve this question. This is also a very straightforward question. So I will discuss the solution now. So this is x, this is xz, this is xy, this is yz. Okay. So this is equal to, we can take x common. So 1 plus y plus z plus yz. So suppose I have any signal y or z. If I add it with 1, it is always 1. So by addition, this is actually OR operations. Okay. So whenever OR operation is performed, the output signal will always be 1. So there are a couple of things to keep in mind. Suppose there is a signal A. If I OR it with signal 1, it will become 1. If I OR it with 0, it will become the same signal. Fine. If I add it with 1, it will be A itself. And if I add it with 0, it will be 0. Fine. So this becomes 1. So this is the answer. I hope the question is clear. So I will give you 5 minutes to solve this question. So the hint will be first make K-map, then obtain simplified logic, and then compare. So I will discuss the solution in 2 minutes. So let's look at the solution. So the expression is So we have 1, 2, 4, and 7. Okay. So in this case, you can see that uh, there is no way we can simplify this logic using KML, and this basically shows that XOR gates will be used. Okay. So so we can take C1 common. Mm, okay. So I think there is a network issue from my side. So is the solution clear to everyone? We have simplified the expression. Then we figured out that we cannot simplify further using KML. So this is the expression. This is 1, this is 2, this is 4, and this is 7 mean terms. Okay. Then we club them together. Fine. This expression is basically XOR operation. Okay. So which we have represented here. Fine. So as you can see, this term repeats again, and this is A and A bar. So this is again a XOR operation. If I have B XOR C, this is basically B C bar plus B bar C. Okay. So in that we get this. So this means that uh, all the three signals are XORed. So only in option A, all three signals are XORed. So I hope this is clear to everyone. Is there any doubt? I hope there is no doubt. I'm moving on to the next question.
What is the answer of question number three? Tell again.
Okay. So whenever we get this kind of expression to simplify, we go for the K-map. So this is the K-map. Okay. And in the K-map, what we do is that we pair all the number of ones together to simplify the logic. But in this case, as you can see, that the ones are diagonally separated. Okay. If you have 1 and 1 in this way, you can club them together. Okay, which is not possible here because they're diagonally opposite to each other. So using K-map, we cannot simplify this logic. So here we wrote down the logic. Okay. Now, if you look at these two expressions, I can take a bar as common. So now my expression will be a bar into b bar c plus bc bar. Okay. And we know that this is the OR operation. Okay. B is OR C, which is represented as bc bar plus b bar c. So here I have replaced it with XOR operator. Similarly, here, as you can see, the expression has repeated again like a bar. Actually, yeah, there's a mistake here. So I will come. Okay, mistake in K map. I will come back to this later. 100 is 4. Okay, yeah. Actually, uh, I made a mistake at this point. After 0 1, it should be 1 1 and then 1 0. So the placement is correct actually. The K map is correct. I actually numbered these two incorrectly. 6 and 7. So in the interest of time, I will come back to this question later. I think we should move ahead to the next question. So I will give you 5 minutes to solve this. So I will discuss the solution. This is a very simple question. A is 110, 1100. B is 1010. If we make a to development, it will be so in this case it will be 0. So 10 it will be 1, then 1, and 0 will also be 1. So the answer will be B. Okay. I hope everybody got this answer. Moving on to the next question. So I will discuss the solution. Suppose that two inputs A, B, then I will have, so what are the possible combinations I can add them, and what will be the output? This is actually very wrong. So if I add two 1-bit numbers, my output will be a 2-bit number, right? So it is the maximum it can go. So I will have two inputs and two outputs. Fine. I hope the question is clear. The question is that the output y, this is the output, has to be always good. So what are the required conditions? So I will give you about 5 to 6 minutes to solve this question. So I will be giving 2 more minutes. This is a fairly easy question. Everybody should be able to solve it. I will discuss the solution now. Okay. At this node, it will be EQ bar. At this node, it will be QR bar. This is PR bar. Okay. So this node, this is EQ bar dot QR bar 4 bar. Fine. Suppose A and B are two signals to NAND gate. The output is AB bar, right? So these two are output from the previous gates. Okay. One is this, another is this. I hope this is clear. Now, for any gate, if this is a NAND gate and the inputs are same, okay. So what will be the output? So if you look at the NAND truth table, so these two cases are not possible because both the inputs A and B are shorted. Okay, so we won't consider them. If you look at these two, you will see that whenever the input is 1, the output is 0, and whenever the output is 0, whenever the input is 0, the output is 1. So it basically behaves as an inverter. Okay, so at this node, we have this term and this term whole bar. So I can write this as PQ bar and with QR bar. Okay, I think this makes sense because this is inverted. This bar shows that this is inverted. If you invert it again, this will be the same expression. Fine. Now we have PQ bar, and with QR bar, here we have PR bar. Okay, PR full bar, and we are passing it through this gate, final gate. So we are passing it through sixth NAND gate. Okay, so the expression will be like this, similar to this. So if we simplify it, it will be okay. First, we will simplify this expression. Okay, so it will be P bar. So it will be Q bar plus P bar R bar. Fine. So we can write this down as Q bar plus P bar R bar P R bar whole bar, which we can simplify as Q bar plus P bar R bar whole bar plus P R bar bar. Like suppose this is A and this is B. So A B bar can be written as A bar plus B bar. This is from De Morgan's law. Okay. So we have done the same thing over here. And if we take invert of an invert, this will basically be PR. Now we have Q bar plus P bar R bar whole bar plus PR. Now simplifying this expression, if I have A plus B bar, it will be A bar plus B bar. This is also from De Morgan's law. So this we can write as Q bar bar dot whole bar plus PR. Now we can write as invert of the invert will be the same value. Now this we can apply this formula. So it will be P bar P double bar plus R double bar plus PR. So this is Q P plus R plus PR, which is QP plus QR plus PR. Okay. So for the output to be always 1, so we can write Y as PQ plus QR plus PR. Okay. So if this is 1 or if this is 1 or if this is 1, my output will always be 1. For this has to be 1, P has to be 1 and Q has to be 1. R can be 0. Similarly here, P can be 0, QR has to be 1. Here, Q can be 0, PR has to be 1. Okay. Or all of them can be 1. So this is your solution. Okay. So option B says two or more of the inputs PQR can be 1. So this is the answer. Fine. Right now, we can get back to the this question. Combinatorial circuit implementation for the following Boolean function. So in this, I think I made one mistake. The mistake being that the KMF was wrong, due to which this expression was wrong. So we will rewrite the expression. So the expression will be so this is your 1, this is 2, this is 7, this is 4. Okay, now uh, we can take C bar common from this expression, from these two terms, C bar A bar B plus A B bar. Now we can take C common from here, so it will be A bar B bar plus AB. Now if I'm writing B or C, it would be BC bar plus B bar C. Okay, so as you can see, this is A bar B plus AB bar, so I can write A or B plus C, A bar B bar plus AB. Now suppose if this expression, if this term is A or B bar, then the entire expression can be written as C bar A or B plus C A or B whole bar. Fine. So now I think we need to show that A or B whole bar equal to A bar B bar plus AB. So this we can do. So A or B whole bar equal to A B bar plus A bar B complement, which will be this is from De Morgan's law. Okay. Fine. So here I applied. Here I applied. I think reverse. Okay. So this can be written as A bar B, sorry, A bar plus B into A plus B bar, which will be, and as I mentioned earlier, this will be 0, this will be 0. Okay. So we have, so this means that this expression, if you look at this expression, this is same as this, which means this is A or B complement. Okay. So we can write them as C bar is or B plus C is or B whole bar, which is equal to, if you keep this signal as x, so this is equal to C bar x plus C x bar, which can be written as C XOR x, which is equal to C XOR A XOR B. Fine. So this is the answer. So option A is the answer. Is that clear to everyone? If there are any doubts, let me know. So the one who asked this question, is it clear to him? So fine, I will move on to the next question. I hope it is clear. I will give you 3 to 4 minutes to think about this question. Can you give a thumbs up? Is it still back? Uh, like I am audible, right? But my voice is not clear. Is it?
Hello.
Hello.
Hello. Is my voice clear now?
Okay.
Okay. Fine. So I'm proceeding. Okay. So uh, suppose this is the circuit I have right now. This is a very common combinatorial circuit. Okay. Combinatorial circuit. We have three NAND gates. Uh, three NAND gates. One NOT gate. Okay. One inverter we have. Fine. So this A and B is the input to this NAND gate 1 and X is the output. Suppose we name it as X. Now um, and here B complement goes because there is a NOT gate and we have C. Suppose the output here at this point is Y. Okay. And X and Y are the inputs to gate 3 and the final output is Z. Fine. So uh, let's look at each of the nodes. What happens? Suppose my original signal is A as 1, B as 1 and C as 1. Okay. So what will be the X value? So 1 and 1 will give me as 0, right? And okay, wait a second. Let's keep B bar as well. Okay. Mm, this is B bar. So if B is 1, B bar is 0. So X is 0 and Y will be 0 and 1. So it will be 1. Okay. And X and Y are inputs to NAND gate 3, which will give Z as output. So the output will be, if you have 0 and 1, the output will be 1. Okay. So suppose I do a sudden transition. Okay. I perform a sudden transition of B from 1 to 0. Okay. Clear. So right now I'm explaining what is this hazard problem. Okay. I'm explaining hazards. So when I make a transition of B from 1 to 0, so this has B has gone from 1 to 0, but as you can see that the input to NAND gate 2 is not directly attached to B, it comes from an inverter. Okay. So inverter will always have some delay. Fine. So it will take time for at this node to go to 1. Initially it is 0 because B was 1, so this node was 0, and when B went from 1 to 0, so this will go from 0 to 1, but it will take some time. So suppose, let's say before that happens, this is 0 and at the same time B bar will also be 0. Is this point clear? that B and B bar can both be 0 at the same time, because the transition will take certain time to reflect. Suppose in later instant, this will still be 0, but this will become 1. Okay, so there will be a transition time. It will take some time for it to reflect. Now let's do analysis for this. So A is still 1, fine, and C is also 1. So in this case, X will be so we have 1 and 0, so X will be 1 only, right? Now we have, in case of Y, okay, initially this will remain at 0, okay, so the output will be 1 only, okay. It will take time for it to reflect. Later it will go down to 0, because this node will become 1. So later it will be 0, but for the very small time instant, this will be 1, fine. And these two are input for the gate 3. So in this case, the output will be 0, and in this case, the output will be 1. So you will see a glitch, okay. So this is the glitch. This glitch is the reason for hazard, okay. So there can be static hazard, there can be dynamic hazard. So our goal is always to remove all the static hazards, because it automatically removes most of the dynamic hazards, okay. So the question says the dynamic hazard problem occurs in, so this is a combinatorial circuit, and I have shown you right now a dynamic hazard, okay. So this problem is present in combinatorial circuit, fine. Now we have, what is sequential circuit? So sequential circuit has a memory component, okay, which can either be in the form of flops. So a simple sequential circuit is basically a combinatorial circuit which goes into memory, which is made up of flops, which is fed back to the combinatorial circuit, okay. Fine. So in sequential circuit, you also have combinatorial circuit, which can which has dynamic hazard. So that's why sequential circuit are also affected by dynamic hazard. So the answer is this, A and B. So is this clear to everyone? And actually, I cannot hear your voice, so it would be good if you can um, comment if there are any problems. If there are no problems, I will move on to the next question. You asked a question. If dynamic hazards are majorly present in combinational circuits, so all the sequential circuits are made up of combinational circuits. So yes, in a way, both are affected. I actually did not get your question. So I will give you 3 to 4 minutes to solve this question. So I will discuss the solution right now. Okay. So this point, so our requirement is that AB plus C bar D bar. Okay. So this point is C plus D whole bar. This is an OR operation which can be simplified as C bar D bar. Okay. From the De Morgan's law. Now, if here we get AB and if this is OR, then our job is done because our final output will be AB plus C bar D bar. But here in this case we have A bar and here we have B bar. Okay. So A bar, B bar, these are inputs. Fine. Which are input, these are inputs to G1 gate and the output should be AB. So if you recall, I think we can do this. This is basically NOR operation, NOR of A bar B bar, which will give you A bar whole bar dot B bar whole bar. This is from De Morgan's law, which will be AB. Fine. So the answer is NOR and NOR and OR. Okay. So this is the answer. Option A. Okay. Moving on to the next question. So the question is that what is the primary cause of glitches in digital circuits? Options are manufacturing defects in the integrated circuits, like when the chip is fabricated, there is some defect in the fabrication process, not in the design. Second is variations in gate delays due to process variations. Third is incorrect connections in the circuit layout. And fourth is inadequate power supply voltage. So I will give you 2 to 3 minutes to think. Okay, what can be the possible reasons? I will discuss the solution right now. So the first option says that manufacturing defects in the integrated circuit. Okay. So there are many different kind of defects which is possible when you fabricate a chip. Fine. There can be many shorts. For example, if you are making an AND gate. Fine. So what are the different kind of manufacturing defects I would discuss? Suppose you are suppose you are fabricating this AND gate, simple AND gate. Okay. So what are the possibilities? There is a possibility that when you are, suppose, how would actually this look like? This is a metal. This is a metal line. Okay. This is also a metal line. This will have transistors. An AND gate. Suppose this is a NAND gate. Okay. It will be easier to explain. A NAND gate will look something like this is your NAND gate circuit. Fine. I think this has been discussed in week 4 lecture. This is what you call as pull-up circuit. This is we call as pull-down circuit. So reason it is called pull-up circuit is that the above part is responsible for bringing that F2. The above part is responsible for bringing that F from 0 to 1. Similarly, the below part is responsible for bringing the output value from 1 to 0. Fine. So what are the different kind of defects we are talking about? So the possibility is that these two wires, these are metal wires, right? So they can get short. Okay. So first is that short A and B. So when the metal line is shorted, what will happen? We will get false output. Okay. What is the second possibility? So the second possibility is that A or B, anyone can get grounded. For example, suppose B is the input signal we are sending, but for some manufacturing defect, this position is grounded. So what will happen? That this node will always register 0. Fine. No matter what B signal you send, it will always be 0. Okay. So the output will always be stuck at 1, because because no matter what A is, the NAND output will always be 1. So this is known as stuck at fault. Okay. But these are not the reasons for the glitch. As we discussed earlier, glitch is something like when a false output comes for a very short period of time, okay, which is not actually desired. That happens during transition. So these are different manufacturing defects which look kind of permanent, and these are not responsible for small glitches that happen due to transition. Fine. So option A is not relevant. Okay. So what about option B? So here option B says, so this was about manufacturing defect, right? Fine. So next we have option B, which says variations in gate delay due to process variation. So here is a term which says variation in gate delay. So when we are talking about gate delays, it refers to this logic gates, okay? Logic gates. And the delay is because of process variation. So I think most of you are not aware about this term. What is process variation? So let me give you, let me explain you. The first thing is that when we manufacture a chip, okay? So initially we have a, this is known as die or wafer, okay? Which is circular. This is circular, made up of silicon, okay? And in this wafer, crystalline silicon, okay? Crystalline. And on this silicon wafer, we actually fabricate our chip. Whether it is integrated circuit, whatever it is, we fabricate on this wafer. Fine. And later what we do is that, so so the chip that you see, which is square in shape, is basically extracted from this portion, okay? So in this wafer, how many chips we fabricated? So this is the number you can count, okay? So this portion is actually wasted because we cannot fabricate it completely. Similarly, this is wasted, okay? So the edges we do not consider. So you have to consider all these squares, and inside of them, so these many chips we can extract from a wafer. Fine. So let's suppose this is one chip. This chip, this is one of the chips, okay? From the wafer we actually extract many chips, okay? So this is one of the chips. In this chip, what you will have, so this is about 1 mm, I think about 1.5 mm cross 1.5 mm, okay? Now if you look inside, you will have a very small portion. This portion will consist of your processor, and this portion will have your memory, okay? There will be hierarchy. Fine. You will have your L1 cache very close to processor, then you will have L2 cache, and then you will have L3 cache, okay? So, and this is your processor. This will have combinatorial circuits. So process variation says that when you're manufacturing this big wafer and it has a lot many chips and lot many smaller processors and combinatorial circuits, there is no guarantee that the, suppose the AND gate that you fabricated here, okay, in this chip will be identical to the AND gate that you fabricated here. Fine. There is no guarantee. It will logically perform the same, okay, it will still give you AND operation, but because of some variation in process, because of this process variation, what will happen is that there is a possibility that this AND gate, suppose this AND gate, suppose this is a very simple gate, okay, combination, for simplicity I am considering that there is one circuit which is an AND gate, so there is a possibility that this AND gate behaves faster as compared to the AND gate that is present in this chip. The reason behind is that if you take the course, if you take VLSI course, you will understand that the AND gate is made up of transistors, and the speed of operation is dependent upon the transistor's threshold voltage. Okay, threshold voltage and doping. So this influences your current, and that current determines how fast will your output arrive. So it is possible that here in this portion, the threshold voltage is less, the doping is more, and the current is high, so that the AND gate performs faster as compared to this. So because of this reason, what happens is that this is your entire chip, like this is your entire wafer. You will have many chips, and all the chips will not perform in the same way. So you will have some variations, because of which there is a possibility that glitch can occur. So how this is related to glitch, I will explain. So if you look at this circuit, and this is my inverter, right? So I said that there will be some delay associated with it. So for example, that for B bar, from 0 to 1 transition, it takes suppose delta t time. Fine. So in faster circuits, what will happen is that this delta t will be very small. It will be so small that it will be negligible. Okay. So in those circuits, you will not be able to see the effect of glitch. Whereas in slower circuits, this delta time t, what will happen in slower circuits? In slower circuits, your current is less. So it will take more time for example, in every circuit, we have to either charge this node from 1 to, either we have to charge this node from 0 to 1, or discharge this node from 1 to 0. Okay, so either in charging or discharging, we need current, and the greater the current is, the less time it takes for the result to appear. So what will happen in faster circuit is that current is more, so delta time t for the transition will be less, and the effect of glitch will not be visible at all. If the current is low, the time will be more, and for that much longer duration, we will get this false output. Okay. So this is the reason, like this is what the process variation is, and this can be the primary cause of glitch. If let me explain you process variation in another way. Process variation is a bigger problem than you can imagine. For example, you might have seen that you are purchasing laptops. Okay, you are purchasing two laptops. One is i5. Suppose both are i5, but one can, if you look at the backside of the laptop, you will see the frequency at which the processor can operate. So one laptop shows that the maximum frequency it can go is 1 gigahertz, whereas the other laptop shows that it can go up to 3 gigahertz. Okay, so how does this variation occur? How is it possible that two i5 chips are performing differently? So the reason is that because of process variation. So every operation in the processor is controlled by a clock. Okay, so speed of CPU is determined by the clock frequency. If higher is the clock frequency, higher is the speed of the CPU. And this clock frequency, so somewhere the clock has to come. So in general, one of the ways in which we can make a clock is that we can make a ring oscillator. Ring oscillator is simply inverter connected back to back. So this is a 3-stage ring oscillator. So how does this behave as a clock? This will behave as a clock as, suppose this node, suppose this node is at 1, it is high. So this will be 0. So this will be 1 and this will be 0. Fine. Since this is 0, this will try to make this as 0. So in next iteration, this will be 0, which will make this as 1, this as 0, this as 1, which will again try to make this 1, which will make this 0, and so the pattern will continue. So you will see that we have got a clock over here, right? So this is one way in which we can generate a clock in the circuit. So this is a 3-stage ring oscillator. But you cannot make a 4-stage ring oscillator because 1 0 1 0 and the next output will be 1, which is same as this. So it would not have any oscillatory property. So you will always have an odd stage ring oscillator. So this is how you made a clock. Okay. So in faster CPU, what will happen is that CPU is faster because this transition is taking less time. Okay. So as I mentioned earlier about the delta t time that inverter takes to show the output. So in this case, it will take 3 delta t time. So the clock time period will be 2 into, because half of the time it will be low and half of the time it will be high. So it will be 2 into 3 delta t because there are 3 inverters and delta t is the time of the one inverter. So for a faster circuit, what will happen is that this delta t will be very slow. Sorry, this delta t will be very less. So if you calculate frequency, f clock, which will be 1 by 6 delta t. So if this is less, what will happen? The frequency will go high. So if the clock frequency is high, the speed of the CPU will be higher and we will get a faster CPU. Suppose the chip that I have manufactured is actually slow. So I will get slower CPU. Fine. So you will see that when you go to purchase a laptop, you will find that the processor is same i5, but it will have a different maximum frequency. And what they do is that the CPU with higher frequency, they sell it at higher price, and the one with lower frequency, they sell at lower price. They wanted, suppose this chip, it got up to 3 gigahertz, this went up to 1 gigahertz. Suppose this went up to 2 gigahertz, 2.5. While manufacturing, they wanted all of them to behave the same, but because of the process variation, each chip behaves slightly different. Okay. So in the end, we get a range from 1 gigahertz to 3 gigahertz. So if you extract the chip out of this wafer, you will get a range at which the clock operates. So this is I briefly explained about the process variation and how it impacts us in our day-to-day life. So let's see at other options. So incorrect connections in circuit layout. So as I mentioned earlier, if we have correct connections, we will still have glitch. So this is not the reason. Inadequate power supply. That is still not the reason for glitch. If you have less power supply, what will happen is that transition will take more time. Fine. But this is not the primary reason, okay? This is correct that if we provide less power supply, it will take more time for the transition. But in general, this is the primary reason. Uh, is this clear to everyone? What I have explained? Regarding manufacturing defect, then process variation. Do you have any doubts? If there are no doubts, we can move on to the next question. So I will give you 2-3 minutes to solve this question. The minimum number of 2-input NAND gates required to implement a 2-input XOR gate. Fine. Coming back to the question, you have asked that if the power supply is not adequate, the circuit gate is unable to be on. This could be the other reason that it does not affect the glitches. When we are talking about power supply, suppose this is the, I hope everybody got the question. I scrolled it up. Fine. So when we are talking about power supply, this is VDD, fine, and this is ground. Okay, this is higher voltage and this is lower voltage. So when we are talking about inadequate power supply, we are talking about this supply. It's not visible. This supply, fine. Suppose my VDD is 1 volt. So when I'm saying that inadequate power supply, it means that I'm supplying about 700 millivolts or 500 millivolts. The input to the gate, so this is my gate, okay? This is my PMOS. These are my NMOS. And the input A is going to the gate of this transistor. So this is my transistor and this is the gate. Fine. Similarly here. So this can be 1. And if this is 1 volt, this this can be 1. So if this is 1 volt, what will happen is that this gate will be on, right? If this gate is on, but here this is a NAND gate, right? So in order to do a pull up, suppose we have to make, let's analyze again. I have to make a transition of F from 0 to 1. So in that case, my pull up network, so this pull up network should be on. So either A or B has to be 0. So in this case, if A is 0, these two NMOS are off. So A is 0, so this is on. So what will happen is that if VDD supply is less, the rate at which you pull it up will be less. I don't want to go into details of this because there is a current expression in which you there is a current expression of transistor where the current is dependent upon the supply voltage. So when the supply voltage is less, the current is less. So in that way, in that case, what will happen is that the transition will take more time. So is your so did it solve your doubt? So I will look into this and I will let you know in the next tutorial. Okay. I think that when we decrease the power supply, the transition takes a lot more time. So it should actually increase the glitches. But I will get back to you. Fine. So let's discuss this solution. So I think it should take about 5 NAND gates. But we can go even less. The answer is 4. As you can see here, this is A bar B plus AB bar. So which can be written as A bar, yeah, which can be written as NAND of A bar B and NAND of AB bar and whole NAND. And in order to generate A bar, we will need one NAND. In order to generate B bar, we will need another NAND. Okay. So if this is a signal A, in order to generate A bar, we can use NAND gate like this. I think right now I'm unable to solve it. I will get back to you in the next tutorial. Fine. So I will end the recording right now. The session ends here. If you have any other doubt, let me know.